Let us do example number 2.2. Example number 2.2 is just like example number 2.1. The only difference between example number 1 and example number 2 is that there is no voltage source in the second loop of this particular circuit. So anyhow, we are going to find out the power consumed by the entire circuit and the power supplied by the voltage source. There are two loops in the given circuit diagram. Here is loop number 1 and here is loop number 2. So we are going to consider the standard loop equations directly in the matrices format, and the size of the R matrix will be 2 by 2. So we consider the standard loop equations for the circuit of example number 2.2 in the matrices format. So these are the standard loop equations in matrices format for the given circuit diagram. The size of the R matrix is 2 by 2. Why? Because there are two loops in this particular circuit. So we have R11 okay. So we have R11, which is the total self-resistance of loop number 1, R12, which is the resistance of the resistor belonging to loop number 1 and loop number 2. R21 is equal to R12, and we have R22, which is the total self-resistance of loop number 2. We shall calculate I1 and I2 with the help of Cramer's rules. We shall find out E1 and E2. E1 is the total voltage in loop number 1 and E2 is the total voltage in loop number 2. So we find out R11. You see, there are two resistors in loop number 1, R1 and R2. And the sum of these two is equal to 2 plus 1, which is 3. So R11 will be equal to 3. R11 will be equal to R1 plus R2, that is 3. So R11 is equal to R1 plus R2, which is 2 plus 1, which is equal to 3. So R11 is 3. We know that R12 is equal to R21. So let us consider this R12 in the circuit diagram. R12 is the resistance of the resistor that belongs to loop number 1 as well as loop number 2. So R2 is the member of loop number 1 as well as loop number 2. And the two loop currents are in the opposite direction in this resistor. So definitely there will be a minus sign with the resistance of this resistor. So R12 as well as R21 is minus 1. So R12 is equal to R21 and it is equal to -1. Now we consider R22. R22 is the sum of all the resistances of loop number 2. And you see there are two resistors in loop number 2, R2 and R3. And the sum of the resistance of these two resistors is 3 ohm. We have 2 plus 1. So R22 will be equal to R2 plus R3 and that is equal to 3 ohm. So R22 is equal to 2 plus 1, that is 3 ohm. Now we are going to find out E1 and E2. E1 is the total voltage in loop number 1 and E2 is the total voltage in loop number 2. So you see there is only one source in the entire circuit, and that source is located in loop number 1. And if we consider the direction of the loop current I1, the voltage across this source is a voltage rise. So there will be a plus sign with this voltage, and there is no voltage source in loop number 2. So E1 will be equal to 8 volt and E2 will be equal to 0. Why? Because there is a voltage source in loop number 1, but there is no voltage source in loop number 2. So E1 is 8 volt and E2 is 0 volt. We put these values in these equations. So let us put the values in the standard loop equations. So we put the values. R11 is 3, R12 is -1, R21 is -1, and R22 is 3 as well. We shall find out I1 and I2 with the help of Kramer's rules. E1 is 8 and E2 is 0. So we apply the Kramer's rules to find out I1. And I1 is equal to 3 ampere. So what we do, we replace the first column of the R matrix by E1 and E2. The second column remains unchanged. We divide this determinant by the determinant of the R matrix, and the determinant of the R matrix is 8. So anyhow, the current I1 is 3 ampere. We compute the current I2. For the current I2, we replace the second column of the R matrix by E1 and E2, and we divide this determinant by the determinant of the R matrix, and the determinant of the R matrix is 8. So the current I2 comes out to be 1 ampere. So the current I1 is 3 ampere and the current I2 is 1 ampere. So the current through the 2 ohm resistor of loop number 1 is I1, that is equal to 3 ampere. The current through the 2 ohm resistor of loop number 2 is I2 and that is 1 ampere. The current through the 1 ohm resistor is I1 minus I2. This resistor is a member of loop number 1 as well as loop number 2, and these two currents are in the opposite direction in this resistor. So the net current through this resistor will be I1 minus I2, that is 2 ampere. So the power consumed by the 2 ohm resistor of loop number 1 will be equal to I1 square, that is 9, multiplied by R1, that is 2. So 9 multiplied by 2 gives you 18 watt. This much power is consumed by the resistor R1. The power consumed by the 2 ohm resistor of loop number 2 is P2, and that will be equal to I2 square, that is 1, multiplied by 2. So 1 multiplied by 2 is 2 watt. So the power consumed by the 2 ohm resistor of loop number 2 is 2 watt. Let us find out the power consumed by 1 ohm resistor. So the current through 1 ohm resistor is 2. So the square of this current is 4. 4 multiplied by 1 is 4 watt. So I square R gives you the power. So we have 4 into 1, that is 4 watt. Now the total power consumed by the entire circuit will be equal to P1 plus P2 plus P3. So P1 plus P2 plus P3 gives you the total power of the entire circuit, the power which is consumed by the entire circuit, and that is 24 watt. So the entire circuit consume a total power of 24 watt. Now let us compute the power supplied by the source. So the power supplied by the source will be equal to voltage across the source, that is E1, multiplied by the current in the source, that is I1. So if you look at the values, so you see the current in the source is 3 ampere and the voltage across the source is 8 volt. So 8 multiplied by 3 gives you a power of 24 watt. So the power supplied by the source is 24 watt. The power supplied by the source is 24 watt. So the power consumed by the source is 24 watt and the power supplied by the source is 24 watt as well. Let us do another numerical example. So we do another numerical example. These examples are from my personal book. So let us do example number 2.3. Here is example number 2.3. Consider the circuit in figure 2.4. Apply standard loop equations to calculate the currents in resistor R1. So we need to find out the current in this resistor. R3, the current in this resistor. R5, the current in this resistor. And you see, we know that the current in this resistor is I1. The current in this resistor is I2. And the current in this resistor is I3. So in this numerical example, we need to find out the current I1, I2, and I3. As there are 3 loops in the given circuit, here is loop number 1, here is loop number 2, and here is loop number 3. So the size of the R matrix will be 3 by 3. So we are going to write down the standard loop equations directly in the matrices format, and the size of the R matrix will be 3 by 3. So we consider the standard loop equations in the generic form. You see the size of the R matrix is 3 by 3. We shall find out I1, I2, and I3 with the help of Kramer's rule. E1 is the total voltage in loop number 1. E2 is the total voltage in loop number 2. E3 is the total voltage in loop number 3. So these are the standard loop equations in the matrices format for the given circuit. We find out R11. R11 is the total self-resistance of loop number 1. So let us consider the total self-resistance of loop number 1. You see there are two resistors in loop number 1, R1 and R2. And R1 plus R2 is 2 plus 2, that is 4. So R1 1 will be equal to 4 ohms. So R1 1 is 4 ohm. There are two resistors in loop number 1, that is R1 and R2. So R1 plus R2 is 4. This is the total self-resistance of loop number 1. We know that R12 is equal to R21, and this is the resistance of the resistor that belongs to loop number 1 and as well as loop number 2. So we consider the resistor that belongs to loop number 1 as well as loop number 2. So R2 is a member of loop number 1 as well as loop number 2, and the two currents are in the opposite direction through this resistor. I1 is in the downward direction, I2 is in the upward direction. So there will be a minus sign with the resistance of R2. So R12 is equal to R21, and that is equal to minus 2 ohm. Now we are going to find out R13. R13 is the resistance of the resistor that belongs to loop number 1 as well as loop number 3, and we know that R13 will be equal to R31. So you see here is loop number 1 and here is loop number 3, and there is no resistor that belongs to loop number 1 as loop number 3. So R13 as well as R31 is 0. R13 as well as R31 is 0. Now we are going to find out R22, that is the total self-resistance of loop number 2. So there are 3 resistors in loop number 2. There are 3 resistors in loop number 2. We take the sum of all these resistance. So you see R2, R3 and R4 belongs to loop number 2. So R2 plus R3 plus R4 gives you 2 plus 1 plus 2, that is 5 ohm. So R22, that is the total self-resistance of loop number 2 is 5 ohm. So the total self-resistance of loop number 2 is 5 ohm. This is the total self-resistance of loop number 2, that is 5 ohm. Now we consider R23. We know that R23 is equal to R32, and this is basically the resistance of the resistor that belongs to loop number 2 as well as loop number 3. So let us consider the resistor in the given circuit diagram that belongs to loop number 2 as well as loop number 3. So R4 is a member of loop number 2 as well as loop number 3, and the two loop currents are in the opposite direction in this resistor. I2 and I3 are in the opposite direction through this resistor R4. So the resistance of this resistor will be negative. So R23 will be equal to R32, and that is equal to minus 2. So R23 is equal to R32, and there is equal to minus 2 ohm. Now we find out R33, that is the total self-resistance of loop number 3. And you see there are 2 resistors in loop number 3, a resistor of 2 ohm and a resistor of 2 ohm. So the sum of these resistance will be equal to 4 ohm. Anyhow, let me consider these 2 resistors in the circuit diagram. So here is loop number 3, and you see there are 2 resistors in loop number 3, R4 and R5, and the sum of these 2 gives you 4. So R33 is 4. So we are done with the elements of the R matrix. Now we are going to find out E1. So you see, there is only one voltage source in the entire circuit, and this voltage source is in the loop number one, and the current in this source flows from the negative terminal towards the positive terminal. So this voltage is a voltage rise. There will be a plus sign with this voltage source. So E1 will be equal to 10 volt. There will be a plus sign with this voltage. Why? Because this is a voltage rise. There is no source in loop number 2. E2 will be 0. There is no source in loop number 3. E3 will be 0. So E1 is 10 volt. E1 is 10 volt. E1 is 10 volt. There is no voltage source in loop number 2 as well as loop number 3. Therefore, E2 and E3 will be equal to 0. So we put all these values in the standard loop equations, and the standard loop equations are in the matrices format. So we put the values in these equations. So let us put the values in these equations. We put the values in this equation. You see, R11 is 4, R12 is minus 2, R13 is 0, R21 is minus 2, R22 is 5, R23 is minus 2, R31 is 0, R32 is minus 2, R33 is 4. We shall find out I1 and I2 with the help of Cramer's rules. E1 is 10 volt, E2 is 0, and E3 is 0. So what we do, we find out the determinant of the R matrix. So let us find out the determinant of the R matrix. So here is the determinant of the R matrix. If we find out the determinant of the R matrix, the determinant of the R matrix turns out to be 48. The determinant of the R matrix is 48. So we have calculated the determinant of the R matrix. So let us apply the Cramer's rules to find out I1, I2 and I3. We apply Cramer's rules to find out the current I1, the current I2 and the current I3. You see, for the current I1, we replace the first column of the R matrix by 10, 0, 0. The second column of the R matrix remains unchanged. The third column of the R matrix remains unchanged. We divide this determinant by the determinant of the R matrix, that is 48. So the current I1 comes out to be 3.33 ampere. We find out the current I2, and for the current I2 we replace the second column of the R matrix by E1, E2 and E3. The first and the third column remain unchanged. We divide this determinant by the determinant of the R matrix, that is 48. So 80 divided by 48 gives you a current of 1.67 ampere. So there is a current of 1.6 ampere in the second loop, and this is the current in R3 as well. We are going to find out the current I3 with the help of Cramer's rules, and for the current I3 we replace the third column of the R matrix by E1, E2 and E3, and we divide this determinant by the determinant of the R matrix, that is 48. So we get a current of 0.833. So the requirement currents are 3.333 ampere, 1.67 ampere and 0.833 ampere. Let us do another numerical example. So we do another numerical example. Consider the circuit in figure number 2.4b, apply standard loop equations to calculate the current in R1, R3 and R5. So this circuit diagram is just like the circuit diagram of example number 2.5. There are three loops. There are three loops in the circuit. The size of the R matrix will be 3 by 3, and the current in R1 is I1. We shall calculate the current I1. The current through R3 is I2, so we shall find out the current I2, and the current through R5 is I3. So basically, we are going to find out the loop currents I1, I2 and I3, and these loop currents are the current through the resistor R1, R3 and R5 respectively. So let us find out these three currents with the help of standard loop equations. So these are the standard loop equations in matrix format for the given circuit. The size of the R matrix is 3 by 3. Why? Because there are three loops in the circuit. We shall find out the current I1, I2 and I3 with the help of Kramer's rules. E1 is the total voltage in loop number 1, E2 is the total voltage in loop number 2, E3 is the total voltage in loop number 3, and you see there is only one voltage source in loop number 1, there is no source in loop number 2, and there is no source in loop number 3. So E1 will be 50 volt, E2 will be 0, E3 will be 0. So anyhow, we are going to find out R11. So let us find out R11. You see there are two resistors in the first loop, that is R1 and R2. So R11 will be equal to R1 plus R2, that is 6 plus 5, that is 11 ohm. We know that R12 will be equal to R21. So that is, you see R2 is a member of loop number 1 as well as loop number 2, and the two currents I1 and I2 are in the opposite direction through this resistor. So there will be a minus sign with R12. So R12 that is equal to R21 is minus 5 ohm. Then we find out R13. So if you look at the circuit diagram, here is loop number 1, here is loop number 3. There is no resistor that belongs to loop number 1 as well as loop number 3. So R13 will be equal to 0. Right? So anyhow, you know how to find out, you see, the elements of the R matrix. Let us go ahead and let us talk about the elements of the R matrix for the given circuit diagram. So we consider R11. You see, R11 is the total self-resistance of loop number 1. We have already calculated this R11, that is 11 ohm. R12 is the resistance of the resistor that belongs to loop number 1 as well as loop number 2. And you see this resistor of 5 ohm belongs to loop number 1 as well as loop number 2. There is a minus sign with this resistor. Why? Because the two loop currents I1 and I2 are in the opposite direction through this resistor. And if you consider loop number 1 and loop number 3, there is no common resistor between loop number 1 and loop number 3. Therefore, R13 will be equal to R31, that is 0. Now we are going to find out R22, and for R22 we calculate the sum of all the resistances of loop number 2. And you see there are three resistors in loop number 2. So if we consider the resistors of loop number 2, R2 plus R3 plus R4, this is the total self-resistance of loop number 2. There are three resistors in loop number 2. So we have 5 plus 4, that is 9. 9 plus 18, 27. So R2 2 is 20 7 ohm. And then we find out, you see, R23, the resistor that belongs to loop number 2 as well as loop number 3. There will be a minus sign with the resistance of this resistor. Why? Because the two loop currents are in the opposite direction through this resistor. You see, I2 is in the downward direction, I3 is in the upward direction through this resistor. So this resistance will be, this resistance will be minus 4, it is not minus 5. So let me erase minus 5, and R23 in this very case will be minus 4. This resistor belongs to loop number 2 as well as loop number 3. And then we find out, you see, R33. So R33 is the total self-resistance of loop number 3. There are two resistors in loop number 3, R4 and R5. We take the sum of these resistance, that is 4 plus 4, which is equal to 8 ohm, right? So you know how to calculate the elements of these the elements of the R matrix now. So R22 is 27. This is the sum of all the resistances of loop number 2. This is the total self resistance of loop number 2. R23 is equal to R32, and this is the resistance of the resistor that belongs to loop number 2 as well as loop number 3. And then we have already calculated R33. So R33 is 4 plus 4. There are two resistors in loop number 3. So 4 plus 4 is 8. R33 is 8. There is only one voltage source in the entire circuit, that is in loop number 1. The voltage across the source is a voltage rise. So E1 is 5 volt. There is no voltage source in loop number 2 as well as loop number 3. So E2 and E3 will be equal to 0. So we put the values in we put the values in the standard loop equations. So here is R11. R11 is 11. R12 is minus 5. R13 is 0. R21 is minus 5. R22 is 27. And R23 is minus 4. R31 is 0. R32 is minus 4. And R33 is 8. E1 is 50. E2 is 0. And E3 is 0. So these are the standard loop equations in the matrices format for the given circuit diagram. We apply the Kramer's rules and we find out the loop currents I1, I2 and I3, and these are the required currents. So what we do, we find out the determinant of the R matrix first. So the determinant of the R matrix is 2000, right? The determinant, if you calculate the determinant of the R matrix, the determinant of the R matrix is 2000. Let us calculate the current I1. For the current I1, we replace the first column of the R matrix by E1, E2 and E3. The second column and the third column remains unchanged. We divide this determinant by the determinant of the R matrix, that is 2000. So there is a current of 5 ampere through this resistor R1. Then we find out the current through the resistor R3, that is I2. For the current I2, we replace the second column of the R matrix by E1, E2 and E3. The first column and the third column remain unchanged. We divide this determinant by the determinant of the R matrix, that is 2000. So there is a current of 1 ampere through this particular resistor. Now we are going to find out the current through R5, that is I3, and what we do, we replace the third column of the R matrix by E1, E2 and E3. We divide this determinant by the determinant of the R matrix, that is 2000. So we get 1000 by 2000. There is a current of 0.5 ampere. So the current I1 is 5 ampere, the current I2 is 1 ampere, and the current I3 is 0.5 ampere. We shall talk about the standard node equations in the upcoming class. Thank you so much.